I am in my living room watching the snow come down. Share screen. Okay, we should have been in class. Let's see what's going on here. Lab started last week. If you missed the first week of lab, you have until this Friday at 10:20 to finish it and get that in. You just won't have any help in lab this week. This week they will only help you with lab 2. So we're going to start lab 2. It's a 3-week lab. There are 3 activities. So if you do 1 activity a week, you're doing pretty good. That's what we expect. Don't wait until the last week to do all 3 activities. It will drive you batty. Homework 3, homework 2 is due today. Homework 3 is due a week from today. Right, there's no lab due, but we're going to keep on going with lab 2. Lab 3 is a 1-week lab. It is the only lab that is completely devoted to MATLAB, the other one. Okay, if you need extra tutoring resources for this class, because we go through the material kind of quickly, it's easy to get behind. The Student Success Center can probably line you up with somebody. IEEE is a good resource too. A lot of people have survived their electrical engineering curriculum by living in the IEEE room. And we may do some tutoring sessions too through Zoom as the semester progresses. That was one of the ideas we had. Now we've gone through the theory of how to do these circuits, and we kind of worked through some of them, but today I just want to work examples. And next class, since I got an extra day, what we're going to do is work on initial conditions and again, working some more problems. These are long problems. It takes a while to get the hang of them. But basically, all I have is my finger now. What we do, we go through and we calculate alpha and omega. Well, first thing we have to figure out is it series or is it parallel? And if it's series, I calculate alpha like this. If it's parallel, I calculate alpha like this. Fairly simple. For both series and parallel, I calculate omega naught. Once I've calculated alpha and omega naught, we figure out, are they greater, are they equal, are they less than? I'm going to go, hold on. See, this is what happens when I'm at home. My attention span goes to 0. There's so many more interesting things to do around. Okay. So I calculate alpha and omega naught. I determine the type of damping. Once I know the type of damping, this is the form of the solution for whichever type of damping I have. If I'm solving for I of t equals A1 e to the S1t plus A2 e to the S2t, etc. That's the form of the solution for whatever I'm solving for. In addition, if I'm overdamped, I'm going to need to calculate S1 and S2. And yes, it matters which one you choose for S1 and S2, plus for S1, minus for S2. If I'm underdamped, I'm going to need to calculate omega D. If I'm critically damped, I'm done with that part. So the next part is trying to figure out how to calculate A1 and A2. This is slide 2 of my key slides. What I do there is I go to this set of equations. If I'm overdamped, whatever variable I'm solving for, that could be, oh great, now I have to write. That could be a current. I just wrote an I there. So it doesn't have to be a V, it could be an I. That variable at time t equals 0 plus is A1 plus A2 if I'm overdamped. The rate of change of that variable at t equals 0 plus is A1S1 plus A2S2. You solved for S1 and S2. Now you've got two equations and two unknowns if you know those initial conditions. Same thing with critically damped, different set of equations. I still have to know the initial conditions. And we'll deal with a little bit of that today. Underdamped, I need to know those initial conditions. Now, how do we get the initial conditions? We've got this wonderful equation, I equals C dV dt. If I solve that for VC dVC dt at t equals 0 plus, I get IC of 0 plus at over C. If I solve this equation for di dl dt and evaluate it at time t equals 0 plus, I get the initial voltage on the inductor over L. Now, from our t equals 0 minus circuit, we get VC of 0 minus, we get IL of 0 minus. Those, and I didn't freeze, thank goodness. Okay, those translate, VC of 0 minus is going to stay constant across an infinitesimal time barrier because it takes time for charge to move. And it takes time for a magnetic field to change, so IL of 0 minus equals IL of 0 plus. Now, the current through a capacitor can and will change really rapidly. That's why we use them. The voltage across an inductor can and will change extremely rapidly. That's why we use them. So to get this VL of 0 plus, we don't know anything about it. For this equation, we're going to have to do a little bit of circuit analysis and simple circuit analysis. To get this IC of 0 plus, we're also going to have to do a little bit of circuit analysis. Now, the dreadful thing is, and you get to do this in the lab, not on the homework, and not on if you're solving for the current or voltage across a resistor, you have no relationship between IR of 0 minus and IR of 0 plus, because it does not store energy, and BR of 0 minus and BR of 0 plus, those can both change. The voltage and current across a resistor can change instantaneously. Okay, I think I got one more piece slide. So this is the circuit analysis part that we're going to have to do. If I have a series circuit, I'm going to know VC because that can't change, and I'm going to know IL. Okay, if I know IL because it's in series, I've got IR. Once I get IR, I can use Ohm's law. Ohm's law. Did I freeze? No, I didn't. My finger's just not working. Ohm's law to find the voltage across the resistor, because we know it's current. My handwriting's going to be really bad today. I don't have my stylus. If I know the voltage across the resistor and the voltage across the capacitor, I'm going to use KCL to find VL. Let's see if there's something else I can use. All right. We'll wing it. Okay, if I'm going a parallel circuit, again, I know, no, that doesn't work. I need my finger. I know VC. I know IL. Now, things in parallel have the same voltage, so VR is known. That is my finger. Okay, so VR is known. If VR is known, then I can calculate IR using Ohm's law. And I know the sum of the currents has to equal 0, so IR plus IL plus IC equals 0. That's the circuit analysis part. We'll do a little bit of that today. Yeah. Now, here's an example. We want to find IL of t for t greater than 0. And we're given RC and L. And I'm giving these initial conditions down at the bottom. There we go. VC is negative 100 volts and IL is 0.5 amps. So we've already solved the 0 minus circuit. It's series, so alpha is R over 2L. We can calculate alpha by plugging in 250 ohms and whatever the heck L is. I've got it written down here. 5 henries. So we plug into that formula, we get alpha is 25 and the units are nepers per second, NP per second. Then we go through and we calculate omega naught. This thing's touchy. Omega naught. Omega naught is 1 over the square root of LC. I plug in those values and I get 20, and it has units of radians per second. They're both dimensionless units, nepers and radians, so you can pretty much equate them. In this case, alpha is greater than omega naught. And because that is true, we are overdamped. Okay, so the form of my solution, I go back to that first key slide. The form of the solution is right here. It's A1 e to the S1t plus A2 e to the S2t. And what am I solving for? I don't know. This is just, okay, this is worse than the stylus. I really want to draw. A1 e to the S1t plus A2 e to the S2t. Next ones I'm doing in bamboo paper. And what was I solving for? I was solving for, I can't see the slide, but this is number 10. I was solving for, yes, I really mean I want to draw with my finger when I touch the screen. It won't let me do it. I was solving for IL of t. So this is the form of IL of t. The next thing we have to do is figure out S1 and S2. So I plug the, if I can get, maybe I can just do this. Sorry, I'm having technology problems. Ah, yay, I can see now. S1 and S2. So I plug it into that equation. I've got alpha and I've got omega naught squared. I come up with S1 is negative 10. S1 equals negative 10. They have units, I didn't even write them down. S1 and S2 have units of nepers per second. This one is much more cooperative, minus 40 nepers per second. Okay, so we've got S1 and S2. We've got the form of the equation. I'm going to write it down again. This is so much better than PowerPoint. It's an E. e to the S2t. Okay, and it will have units of amps. So we've got S1 and S2. The only thing we have left to figure out is A1 and A2. So I'm going to go back to PowerPoint, and this is one of my key slides. I said I have an overdamped system, so my current at 0 plus is going to be A1 plus A2. The derivative of the current at 0 plus is A1 S1 plus A2 S2. So back to here, IL of 0 plus equals A1 plus A2. And if we look at the problem statement, there was that skip. It gave me IL of 0 plus was half an amp. Okay. The tricky part is DIL of 0 plus over L. Wait, DIL, I forget the D. IL of 0 plus over L will be the initial condition on the derivative, equals S1A1 from that set of equations I just showed you, minus 10 A1 minus 40 A2. Now, we don't know what the initial condition, that's VL. We don't know what the initial condition on the voltage is. So now we got to go back and do a little bit of circuit analysis. So I look at this, the voltage across the capacitor is minus 100 volts. Yeah, that's 100. Okay, the current through the inductor is half an amp. So if I've got half an amp through the inductor, I have a half an amp through the resistor. And if I define plus up here and plus over here, no, plus over here, I do KVL around that loop. I've got a half an amp through a 250 ohm resistor. This is 125 volts. And it's going, the current's going the wrong way. So I'm frozen. That's what's going on. I will be back in a minute with my bamboo paper. Hold on, 30 seconds.